Greetings of day to all of you. Well, today I am going to deliver another lecture on electric drives. Today is Monday, 9th January 2023, and I am going to deliver lecture number 5. Well, today I am going to discuss a very important aspect of electric drives, that is steady state stability. Steady state stability. We already know and we have already discussed about torque speed characteristics of different types of loads like a crane, a hoist, an electric traction type of load, fan, pump, blower type load, constant power load, and so on. And similarly, if you study different types of electric motors which are available like DC motors or AC motors, uh, we know about the torque speed characteristics of different types of motors. Well, uh, the when we know about the load torque characteristics, and we also know about the motor torque or speed torque characteristics, it will be very easy for us to determine the operating point. Well, the operating point of an electric drive will be the point of intersection of the two characteristics. We already know that the torque developed by a motor T is equal to load torque TL plus friction torque TF plus J d omega dt, which is inertial torque. Where what is this friction torque? We already know that this friction torque has different components, like it has a static component Ts, plus it has a you know viscous friction component TV, viscous torque, plus it has a constant component TC, plus TW, that is windage component. As far as this viscous friction torque TV is concerned, we can say it is K1 into omega m, and as far as this windage friction torque is concerned, it is K2 into omega m square. Now what happens, this useful load torque and the friction load torque, we combine the two terms and we call the two terms, or we designate or denote the two terms as TL. TL is the total load torque, which comprises of useful load torque, which is used to drive the motor and its driven load, plus the friction torque, where friction torque has all these components. So therefore, the electromagnetic torque developed by a motor should be equal to load torque plus J d omega by dt. This is during the acceleration, that means during the start, or during the deceleration, that means during the stopping of the motor and it is driven load. What happens when the motor reaches the steady state speed? I mean, when you start the motor, the electric drive accelerates, and at that time the total torque to be developed by motor should be equal to load torque plus this inertial torque. Okay, and once the motor has reached the steady state speed, okay, acceleration is over. The say motor has accelerated and finally it has reached the steady state speed. At that time, omega m, that is the speed of the motor, is constant. Okay, so when omega m in the steady state conditions is constant, so J d omega m by dt is equal to 0. So therefore we can write that in steady state, or at steady state, J d omega m by dt, that is the inertial torque, is equal to 0. So therefore the torque which is to be developed by the motor should be exactly equal to the load torque. That means whatever is the load torque requirement, the torque should be developed by the motor. The electromagnetic torque developed by the motor should be equal to load torque in order to keep the load rotating or keep the load in motion, in order to drive the load for doing the useful work. Okay. Now, if you draw the torque speed characteristics of the motor, a particular type of motor and load, where is this operating point? I mean, the operating point is a point where when the motor torque is exactly equal to the load torque. So it is something like this. See, this is the torque axis, torque plotted along x-axis and speed plotted along y-axis, omega m. Let us take a separately excited DC motor. We know that this is the torque speed characteristic of a separately excited DC motor. I will write here separately excited DC motor. This is the torque speed characteristic of a separately excited DC motor. Let me call this torque as T, electromagnetic torque developed by motor. Okay, and let us suppose the load has this type of characteristic. This is the load torque characteristic, TL. We may have a type of load, a particular type of load, in which as the torque increases, the speed also increases, say in a linear fashion like this. And let us suppose this is the torque speed characteristic of the load. So therefore, this is the variation of speed with torque or variation of torque with speed for a load, and this is the variation of speed with torque for separately excited DC motor. Where is the operating point? As per this equation, the operating point is under the steady state condition is the point when electromagnetic torque developed by motor is exactly equal to load torque, and that is this point. This O is the operating point. And at this O, the motor runs at a speed omega m, and this is omega m naught, that's no load speed here. And this is the actual speed of the motor, and it develops this much of torque. Let's call this torque as T. So therefore, O is the operating point. O is the operating point of drive, operating point of electric drive, or operating point of drive. Because at O, you can clearly see that the torque developed by motor is exactly equal to load torque, and hence the drive, the motor drives the load and keeps the load in motion for doing the useful work. Okay, so far so good, no problem. So it is very easy to find the operating point whenever, if you know the load torque speed characteristics, you know the motor torque speed characteristics, you draw the characteristics, the point of intersection of the two characteristics will be the operating point. Now it is not the end of the story. The story begins from here, because the operating point O may be stable operating point or it may be an unstable operating point. What do you mean by stable operating point? A stable operating point is that point at which the drive remains in stable equilibrium. That means if there is any perturbation of speed or torque or supply of the drive, the operating point is not disturbed. Temporarily, the torque or the speed may change. It may increase or it may decrease, but very quickly the operating point will be restored. I mean, the operation will again start at this operating point. On the other hand, the operating point will be unstable if there is a small disturbance or perturbance in torque or speed. The operating point, the motor or the drive will run away from its operating point. To make the things very clear, let me explain it with the help of a few examples. I will take two different cases, or about three cases. This is the torque speed characteristic of motor and load. Let us suppose this is the torque speed characteristic of motor, T. Capital T means torque developed by motor. And let us suppose this is the torque speed characteristic of the load, TL. This point A is operating point, because at point A, T is equal to TL. Okay, and what is the speed corresponding to this operating point? The drive runs at a speed omega m. So this is the operating point. Now we have to verify whether this operating point is a stable operating point or an unstable operating point. For that purpose, we will give a small perturbation to the load torque or the speed. Let us suppose the speed of the motor or speed of the drive increases by a small increment. So this is increase in the speed, delta omega m. Due to some reason, Okay, there is the speed is not, the drive is not running at the rated speed. The speed may temporarily increase due to some disturbance, due to some perturbance in the system. Okay, so therefore what is the new speed? New speed is omega m1 equal to original speed, rated speed, plus speed perturbation or increment in speed, delta omega m. So excuse me, omega m1 is equal to omega m plus delta omega m. Now this operating point will be stable operating point, or the drive will be operating stably only if the operation returns back to operating point, original operating point. Let's see whether this happens or not. When the speed increases and the new speed is omega m plus delta omega m, what is the motor torque? This is the motor torque and this is the load torque. So you can very clearly see at omega m1 equal to omega m plus delta omega m, the load torque is greater than motor developed torque. This is the motor, because this is the torque speed characteristic of motor. So this is the motor developed torque, and this is the torque speed characteristic of load, and this is the load developed torque. You can very clearly see load torque is, this is load torque and this is motor torque. Load torque is greater than motor torque. And when load torque is greater than motor torque, what happens to the drive? Drive decelerates. Okay, it slows down. That means drive slows down. So when it slows down, its speed had temporarily, due to some perturbation, increased. It will slow down and it will come back to its original operating point, and it will run at the rated speed omega m. Okay, so therefore a small increase in speed, temporary increase in speed, it will be a temporary phenomenon. As soon as speed increases by a small increment, delta omega m, load torque becomes greater than motor developed torque. It slows down the drive and comes back to its original operating point A. Similarly, let us assume that there has taken place a decrement in the speed by same amount, delta omega m, so that the new speed omega m2 is equal to original speed, rated speed, minus delta omega m. Originally, the drive was operating at point A, where the rated speed was omega m. There has been a perturbance. Due to the perturbation, the speed has decreased by a small decrement, delta omega m, so that the new speed is omega m minus delta omega m. Now you can see that at new speed, omega m2, which is equal to omega m rated speed minus delta omega m, the drive has slowed down. Its speed has come down by this much amount. What is the load torque? This is the load torque and this is the motor torque. Now we can see here the motor torque is greater than load torque. T is greater than TL. So since motor torque is greater than load torque, the drive speeds up. Since motor is developing more torque than the load torque required, so it causes acceleration of the drive speeds up. It had originally speeded down, so it will speed up and it will go back to its original operating point. So original operating point A is restored again. So in both cases, whether there is increment in speed or decrement in speed due to some perturbance, the original operating point is restored. So hence this type of motor torque characteristic and load torque characteristic gives stable equilibrium operating point. Okay, so point A, we can clearly say that point A is stable equilibrium operating point, or you can simply say that point A is stable operating point, stable equilibrium operating point. Okay, so let us take another example. In the other example, we will have, this is the torque and this is the speed along y-axis. Let us suppose this is torque developed by motor, and let us suppose this is the load torque TL. Fine. So characteristics are different. This is the torque developed by motor and this is the load torque, and this is the operating point. Point B is the operating point, and at this point B the drive is operating at rated speed, say omega m. Let us again give perturbations in the speeds. let us increment the speed by delta omega m and again decrease it by delta omega m, so that this omega m2, omega m1, and the speed has increased by delta omega m. This is delta omega m. Similarly, this is delta omega m. So at this point, the new speed is omega m equal to original speed plus delta omega m. And similarly, at this point, the speed, new speed is omega m2 equal to rated original operating speed omega m minus delta omega m. Let us take the increment in the speed. The drive speed has temporarily increased due to some perturbance. So if point B is the stable operating point, the point B will be restored. Let's see whether it is restored or not. Okay. Let us suppose this is the motor torque and this is the load torque. Okay, so this is motor developed torque speed characteristic, and this is load torque speed characteristic. Now, as soon as due to some perturbance, the motor speed has increased by delta omega m, and new speed is omega m1 equal to omega m plus delta omega m. What happens? This is the new load torque and this is the new motor torque. Now we can clearly see motor torque is greater than load torque. T is greater than at omega m1 equal to omega m plus delta omega m. Motor torque is greater than load torque. So since motor torque is greater than load torque, it will cause further increase in the speed. Okay, the stable operating point should have been, for the stable operating point, the load torque should have been greater than motor torque, so that the drive slows down and comes back to its original operating point. But reverse is the case. The motor torque becomes greater than load torque, so that drive speed, instead of decreasing, it is further increasing. It is accelerating more and more. And therefore, the operating point B will never be restored. The motor and the drive will run away from its original operating point. So therefore, the drive runs away from operating point B. So it never comes back to operating point B. Let us see what happens if due to some perturbance there is a decrease in the speed of the drive. When there is this decrease in the speed of the drive, and new speed is omega m2 is equal to omega m minus delta omega m. Okay, the original operating point B should be restored. Let's see whether it is restored or not. Now we can very clearly see here at new operating point, at new speed omega m2, the load torque is less than, the motor torque is less than load torque. So load torque is greater than motor torque. And when load torque is greater than motor torque, it causes further slowing down of the drive. So the drive will keep on slowing down and slowing down. It will never come back to its original operating point. So this causes slowing down of drive. And hence the drive again runs away from the original operating point. So this statement is true for decrement in speed also. So we can say the drive runs away from operating point B. So therefore, a small perturbance in the speed, a small increment in the speed of the drive or a small decrement in the speed of the drive will cause the drive to run away from its original operating point. The original operating equilibrium point will never be restored. The drive will run away from original operating point. So therefore, point B is not a stable operating point. It's an unstable operating point. So therefore, point B is unstable operating point. It's unstable operating point. So this should be very clear. It is not sufficient that the torque speed characteristic of load, the torque speed characteristic of motor, and the point of intersection of the two characteristics is the operating point. No, it's not always true. No doubt the point of intersection of the two torque speed characteristics is the operating point. As in this case, A is the operating point, in this case, B is the operating point, because at A and at B, T is equal to TL. Okay, so this is the operating point. The question is this operating point stable or not stable? We have taken two different cases. In the first case, we have found that A is the stable operating equilibrium point, whereas in the second case, this case, B is not a stable operating point. It is an unstable operating point. Similarly, if you take the case of torque speed characteristics of, let's take an induction motor torque speed characteristics. This is torque along x-axis and speed along y-axis. The induction motor torque speed characteristics are something like this. This is the starting torque. When you draw torque along x-axis and speed along y-axis, this is the induction motor torque speed characteristics. And let us suppose this is the load characteristic. This is the induction motor torque speed characteristic, T for induction motor, IM means induction motor, and this is the load torque speed characteristic, TL. So let us suppose we have a constant torque load, a load in which torque remains constant. This is the constant torque load. Okay. Now we have here 2 points of intersection. We have point A and we have point B. As per theory, at point A, T is equal to TL. At point B also, T is equal to TL. So we have two operating points. Which one is the stable operating point? Let's try to find out. At A, T is equal to TL. So this is the operating point. If there is a change in the speed, I mean the speed has incremented. Let's see what happens. This is the original operating point, A, at which the speed is omega m. Let us suppose speed has increased by delta omega m. Okay. When the speed has increased by delta omega m, this is the new speed, omega m1. Okay. Now, what about load torque? You can very clearly see now this is the motor torque and this is the load torque. Load torque is greater than motor torque. And since load torque is greater than motor torque, it slows down the machine. Machine had originally, speeded up due to some perturbance, but it slows down the machine and machine comes back to its original operating point. Similarly, let's suppose that there is a decrement in the speed due to some perturbance. When there is the decrement in the speed, now new motor torque is this and new load torque is this. Now we can see motor torque is greater than load torque. Since the drive had slowed down and now motor torque is greater than load torque, it will accelerate, it will speed up the drive and drive will come back to its original operating point A. So therefore A is stable operating point, stable operating equilibrium point, stable operating equilibrium point, or we can say A is the stable operating point. What about B? Apply the same logic at B. Let's suppose at B, this is the rated speed omega m. Let us suppose it has increased by delta omega m. Similarly, it has decreased by delta omega m. Since the speed has increased by delta omega m, new speed is omega m1 equal to omega m plus delta omega m. So the drive has speeded up. Its speed has increased. Okay. Now at new operating point, what is the motor torque? Motor torque is this and this is the load torque. You can see clearly motor torque is greater than load torque. And since motor torque is greater than load torque, it causes further speeding up of the drive. So drive keeps on speeding up and it runs away from its original operating point. Similarly, let's suppose the speed has decreased. It has not increased, it has decreased by delta omega m, so that the new speed is omega m2 equal to omega m minus delta omega m. So the drive has slowed down. Let us see whether it comes back to its original operating point or it runs away. Now at new operating point, this is the load torque and this is the motor torque. Now you can see load torque is more than motor torque, and when load torque is greater than motor torque, it further causes slowing down of the drive. So the drive keeps on slowing down till maybe it comes to a standstill. So therefore it again runs away from its original operating point. So therefore, although B is also an operating point, but B is not a stable operating point. So B is not a stable operating equilibrium point, or we can simply say B is not a stable operating point. It's an unstable point. So therefore the drive will settle at A because A is the stable operating point. This is for constant torque load and induction motor torque speed characteristics. we have two operating points A and B. We have clearly seen that A is the stable operating point, B is not stable operating point. So therefore our drive will run at operating point A, at which the speed will be omega m and the torque developed is equal to the load torque, T is equal to TL. Now let us take on the same torque speed characteristics another type of load, fan type of load. So this is fan or blower type of load, fan or blower or pump type of load. And this is the load torque characteristic. Where is the operating point? This is the operating point. Let's call this operating point as C. And this is the speed at which the drive rotates. Okay. Now if there is an increment in the speed, see there is an increment in the speed of the drive. Now you can see motor torque becomes greater than load torque. This is load torque, this is motor torque, and it causes the drive to run away from the original operating point. Similarly, if there is a decrement in the operating speed, this is the load torque, this is the motor torque. Load torque is greater than motor torque. So since load torque is greater than motor torque, it keeps on decelerating the drive. The drive keeps on slowing down and slowing down. It runs away from its operating point C. So therefore C is not a stable operating point. Stable operating point. Let me check it again. I think there is some mistake I am committing here. Let me check it again whether it is stable operating point or not. Let us see. Let us increase the speed. This is the original speed. Let us increase the speed. See, the speed has increased. I'm sorry, it's a stable operating point. It's not unstable operating point. The speed has increased from omega m to omega m1, where omega m1 is omega m plus delta omega m. So speed of the drive has increased. Now this is the motor torque, and this is, where is the load? Where is the load? This is the load torque, because this is the load torque characteristic. This is intersecting the load torque characteristic here. Now you can clearly see load torque is greater than motor torque. When load torque is greater than motor torque, it causes slowing down of the drive. The drive had originally speeded up. So it causes slowing down of the drive, and drive restores its operating point. It comes back to its operating point. Similarly, if there is a decrement in the speed by delta omega m, so that omega m2 is omega m minus delta omega m, this is the motor torque and this is the load torque. The drive has slowed down. Now this is the motor torque, this is the load torque. Motor torque is greater than load torque, and since motor torque is greater than load torque, it causes the drive to speed up, and hence it goes back to operating point C. So therefore C is a stable operating point. I am sorry, I had earlier said it is an unstable operating point. It is a stable operating equilibrium point, or simply we can say it is a stable operating point. So therefore the fan type of load intersecting with the torque speed characteristics of the induction motor, when the induction motor drives the fan type of load, the operating point is always a stable operating point. Okay, so for constant torque load, A is the stable operating point, B is the unstable operating point, and for fan type of load, for this type of load, C is the stable operating point. There is only one operating point, C, it's a stable operating point. Now let me explain to you that this portion of the characteristic of induction motor, see this is the induction motor torque speed characteristic. So BC characteristic, BC torque speed characteristic of induction motor has positive slope. You can clearly see it. It's like this, it is increasing. When you go from C to B, it is increasing. So it has a positive slope. And for most of the loads, this characteristic, BC characteristic portion of the torque speed characteristic of induction motor, if the load operates on this part, BC part, for most of the loads, this portion is the unstable operating. Although we have just few moments back seen that for fan type or blower type of load, this is a stable operating point, but this is not true for all type loads. If you take this constant torque load, and instead of having it here, you have it here, and you have operating point somewhere here. It will be unstable operating point. As you have seen already, it's unstable operating point for this type of load here. It will be unstable operating point here also. It will be unstable operating point all the way. So this type of characteristic, BC, or even from here to this B, this unstable operating point, because the slope of the torque speed characteristic is a positive slope, and whenever this is the motor torque speed characteristic has positive slope, most probably for most of the loads this is unstable operating, this is unstable characteristic, torque speed characteristic. So therefore BC is statically, it is called statically unstable characteristic, unstable torque speed characteristic for majority of loads, except for a few loads. But for majority of loads, it is an unstable operating point. And then which is the stable operating point? Which is the stable operating torque speed characteristic? This is the stable operating torque speed characteristic, this one, which resembles that of a separately excited DC motor or shunt motor. Whereas this portion of the torque speed characteristic is for majority of loads, it's unstable torque speed characteristic. Okay, fine. Now, so in mathematically we can say that we have taken about 3 examples, and with the help of 3 torque speed characteristics or 3 examples, we have tried to identify which points are stable operating points and which points are unstable operating points. So is it possible that without doing this exercise we can find that a particular operating point is a stable operating point or unstable operating point? Yes, it can be done mathematically. So mathematically, if the rate of change of load torque with speed, if dTL by d omega m minus dt by d omega m is greater than 0, or it means the slope of load torque characteristic with respect to speed is greater than motor torque characteristic with respect to speed, dTL by d omega m, if it is greater than dt by d omega m, or if dTL by d omega m minus dt by d omega m is greater than 0, then the operating point is stable operating point. Then, so if dTL by d omega m minus dt by d omega m is greater than 0, then operating point is stable. On the other hand, if this is negative, that means if dt by d omega m is greater than dTL by d omega m, then the operating point will be unstable. Let us try to prove this. Can we mathematically prove it? Let's try to prove this. Proof. We already know that the torque developed by a motor is equal to load torque plus J d omega m by dt, right? Let us call this equation as equation 1. Let us suppose that due to some perturbance, the torque has got perturbed, motor torque has got perturbed, load torque has got perturbed, and speed has got perturbed. Just few moments back you have seen when the speed is increased by delta omega m or it is decreased by delta omega m, the load torque changes and the motor torque also changes. So due to some perturbance, T B equal to T plus delta T. I mean, it has got perturbed from T to T plus delta T. TL is equal to TL plus delta TL, and this has happened because speed has changed from omega m to omega m plus delta omega m. Let us suppose there has been some perturbance in the speed. It has changed or increased from omega m to omega m plus delta omega m, due to which the motor torque has increased by delta T from T to T plus delta T, and load torque has also increased from TL to TL plus delta TL. So therefore, from equation 1, instead of writing T, we will write T plus delta T under perturbance. T plus delta T is equal to, here it is TL, I will write TL plus delta TL plus J d by dt of omega m. So I will write omega m plus delta omega m. So again I will write T plus delta T is equal to TL plus delta TL plus J d omega m by dt plus J d by dt of delta omega m. This is equation 2. Let us subtract equation 1 from equation 2. Subtracting equation 1 from equation 2, we get, let's see what we get. I'll write here rest of the steps. So it is T plus delta T from equation 1 on the left hand side minus T from equation 2. This is T plus delta 2, which is the left hand side of equation 2, minus T, which is the left hand side of equation 1, is equal to, what is the right hand side of equation 2? It is TL plus delta TL plus J d omega m by dt plus J d delta omega m by dt minus, you have to subtract right hand side of equation 1, which is TL minus J d omega m by dt. So what do we get? Plus T minus T adds up to 0. This is TL plus delta TL minus TL. Okay, I'm sorry, I have forgotten, it is TL minus TL. Okay, because this TL will subtract here. TL minus TL will add up to 0. J d omega m by dt minus J d omega m by dt, they will add up to 0. So what do we get? Delta T is equal to delta TL plus J. Okay, this minus TL is already here. So T plus TL minus TL, they will add up to 0. Okay, so this is delta TL plus J d delta omega m by dt. So this is what we get. So this is the change in torque from T to delta T, T plus delta T. Change in load torque is by delta TL. I mean, it has changed from TL to TL plus delta TL. Similarly, speed has also changed. Okay, let us suppose the change in the torque and the speed is so small that it is given by a straight line. I mean, if this is your original speed, original torque T, T plus delta T is this. So this change or this increment is given by a straight line. Similarly, if this is delta TL and this is, I mean, this is TL and this much is delta TL, new load torque is TL plus delta TL and it is given by a straight line. Okay, so when the change in load torque and change in motor torque is very small, so that they are given or they are governed by a straight line, a linear thing, then this delta T can be written as dt by d omega m into delta omega m, where dt by d omega m is the slope of this curve. This is T and this is T plus delta T, and its slope is dt by d omega m, okay, into delta omega m. Similarly, what is delta TL? Delta TL is dTL by d omega m into delta omega m. So substituting in this equation, let's call this equation as equation 3. So therefore from equation 3 we get, instead of delta T we will write dt by d omega m into delta omega m is equal to, instead of, in place of delta TL we will write this, because delta TL is dTL by d omega m into delta omega m plus then this term J d by dt delta omega m. Okay, fine. Or we can write like this. I will write this term J d by dt of delta omega m plus d by d delta omega m by d omega m TL minus T is equal to 0. I have, you just shift it from left hand side to right hand side. So here it will be dTL by d omega m by d delta omega m by d omega m minus d delta omega m by d omega m. So it will be TL minus t, because you are shifting it to right hand side. Here it is plus, here it will become minus. So this is what we get. So this is a differential equation. You can see j d delta omega m by dt plus d delta omega m by d omega m times d TL minus t is equal to 0. It's a linear differential equation. It's not a non-linear differential equation, it's a linear differential equation, and we know how to solve differential equations. Its solution is delta omega m. We have to find delta omega m, that is the change in the speed, is equal to delta omega m naught, that is the initial perturbance or initial speed, e raised power minus 1 by j times, in fact it is j also here, I have forgotten, we have j also here, j is here, I'm sorry, j is here. So 1 by jm TL minus t, TL 1 by j times dTL by d omega m minus dt by d omega m t. So this is the equation of this linear differential equation. This is the solution of this linear differential equation. Delta omega m is delta omega m naught, that is the initial speed. This is initial perturbance in the speed or initial disturbance in the speed. Then exponent raised power minus 1 by j times dTL by d omega m minus dt by d omega m. Now this is the change in the speed due to some perturbance, due to some disturbance. If the drive is operating at a stable operating point, or if the operating point is stable operating point, then after some time this delta omega m should become equal to 0. I mean, the original operating point should be restored. And when the original operating point is restored, I mean, if the speed has changed from this point to this point, it should come back to original operating point. So that means this delta omega m after some time should become equal to 0. That means as time, this time t tends to infinity, so delta omega m becomes equal to 0. If this happens, then our system is a stable operating, our system is a stable system, and operating point is a stable operating point. So this is time axis, and this is delta omega m axis. This is delta omega m 0, initial change in the speed. Then it should change like this. As t tends to infinity, you can see as t increases from 0, this delta omega m goes on decreasing, and finally at some point, at some value of t, it becomes equal to 0. And when delta omega m becomes equal to 0, that means the drive is now operating at original operating speed, omega m, which was earlier omega m plus delta omega m, but after some time delta omega m has become equal to 0. So original operating speed, rated speed, has been restored. That means we have restored, the drive has restored its original operating point. So that means drive is a stable operating point. The drive is a stable drive. It is operating under steady state stability. It's a stable drive, and the operating point is a stable operating point. Now delta m becoming equal to 0 as t tending to infinity is possible only mathematically when this exponent has negative coefficient. This is the coefficient of exponent. It should be negative. This is possible only, so this means power of exponent. This is the power of exponent should be negative. When this is negative and the power of this e exponent is negative, and what is its power? This is its power. Then only this, as t tends to infinity, delta m becomes equal to 0, and the stable operating point is restored. Now when will be this power of this exponent negative? When this term is greater than this term. That means dTL by d omega m is greater than dt by d omega m. So this is possible only when dTL by d omega m minus dt by d omega m is greater than 0, which also means dTL by d omega m should be greater than dt by d omega m. That means the rate of change of load torque with respect to speed should be greater than rate of change of motor torque with respect to speed, or change of load torque with respect to speed minus change of motor torque with respect to speed. This should be greater than 0. If this condition is fulfilled, then we can say the drive is stable drive, otherwise it is unstable. Which means if both the slopes are positive, but if the slope of load is positive, slope of motor is also positive. But if the slope of load is more positive than the slope of motor torque, I'm talking of torque. If the slope of load torque is more positive than the slope of motor torque, then this condition will be fulfilled and drive will be stable. On the other hand, if both slopes are positive, but the slope of motor torque is more positive than slope of load torque, then this term will be less than 0. And when this is less than 0, then that means dTL by d omega m will be less than dt by d omega m, and drive will be unstable. The operating point will be unstable. So without doing all that exercise which we have done just a few moments back, if you are able to find this dTL by d omega m and dt by d omega m and see whether this condition is satisfied. If this condition is satisfied, the drive is stable. Otherwise, we have unstable drive. The operating point is unstable. This will be clear if we solve one numerical example. I have a numerical example for you. After solving that numerical problem, we will be able to, so this is the numerical problem for you. I will read. It's written here that a permanent magnet DC brush motor with the torque speed curve as omega m equal to 200 minus 0.1 TE drives a DC generator which supplies a resistive load such that the generator torque speed equation is omega m equal to 2 TL. Draw the torque speed characteristics for steady state point and find out if that point is stable. So I will give you this written problem on WhatsApp. Okay, so this is the problem. And let us try to solve it, and let's try to apply this mathematical formulation and try to find whether the drive is permanent or not. So it is simple. We have a DC motor drive. This is DC motor. It is coupled to a load. It is a generator, DC generator, which is driving an electrical some load resistances. The torque speed characteristic of motor is given as, I will write here, motor torque speed characteristic, motor torque speed characteristic is given in the problem itself, and it is given as omega m equal to 200 minus 0.1 T. E, where Te is the torque developed by the motor, and this is the no load speed minus 0.1 times torque. So if you plot this, you will get torque speed characteristic. Let's try to plot it. This will give the torque speed characteristic of motor. This is torque and this is speed. When T is equal to 0, so initial speed, no load speed is 200. So we will start from 200. So omega m is equal to omega m naught, that's no load speed, is equal to 200. Then as you increase the load, as you increase electrical load on the generator has to draw more and more power from the source, mechanical power. So the load torque increases more and more. So therefore the motor also has to develop more and more torque. So this electromagnetic torque developed by motor increases. Say for example, at electromagnetic torque Te equal to 100 Newton meter. If the motor develops a torque of 100 Newton meter, what is the speed of motor? It is 200 minus 0.1 into 100. That is 200 minus 10. That is 190 RPM. Oh, sorry, 190 radians per second. It is not in RPM. It is radians per second. So therefore, for a torque of 100 Newton meter, this is torque in Newton meters, and speed is in radians per second. For a torque of 100 Newton meters, what is the speed of the motor? It is 190 RPM, 190 radians per second. This is 190 radians per second, omega m. Okay, so if you take this, and this is the point, and therefore this is the torque speed characteristic of motor. So this is the torque speed characteristic of motor, which is represented by T. At no load, omega m naught no load speed is 200 radians per second as per this equation. And as you increase the load, electrical load on generator, that mechanical load on the motor increases. That means as you increase the load on the motor by loading the generator more and more, the motor develops more and more torque and its speed falls, so that at a low torque of 100 Newton meter, the motor speed drops from 200 radians per second to 190 radians per second. So it's like this. So this is the torque speed characteristic of motor. Similarly, what is the torque speed characteristic of generator? It is also given. The generator torque speed equation is given by omega m equal to 2TL. I will write here generator torque speed characteristic is, it's given as omega m equal to 2TL. That means when low torque is 0, I mean when there is no electrical load, low torque is 0. When there is no electrical load, generator is not drawing any power from the source. So low torque is 0. So speed, what is speed? Speed of generator, I mean in other words, when the speed of generator is 0, when the generator is running at 0 speed, it develops 0 torque, because at TL equal to 0, omega m is equal to 0. And as TL increases, omega m increases 2 times TL. So that, let us see, at low torque of 100 Newton meter. When low torque is 100 Newton meter, what is speed? 2 into 100. So 200 Newton meters. At TL equal to 0, omega m is equal to 0. So we have to start from 0. Then as TL increases, omega m also increases 2 times TL. So that at TL, that's low torque, equal to 100 Newton meter, which is already a point available on this x-axis. What is omega m? Omega m is 2 into 100. That is 200 radians per second. So for 100 Newton meter, omega m is 200. So this is 200 radians per second. So this is the generator torque speed characteristic. This is generator torque speed characteristic, and this is the load torque TL, because generator acts as a load on the motor. Okay, at TL equal to 0, omega m is 0. Then as TL increases, omega m increases, so that at TL equal to 100 Newton meter, omega m is 200 radians per second. So this is the generator torque speed characteristic. So this is the point of intersection between motor torque and load torque. This is motor torque speed characteristic T, and this is load torque speed characteristic TL. We already know that the point of intersection of the two is the operating point, and this is the operating point. Let's call this operating point as O, and at this operating point, this is the speed. Let us try to find out speed at this operating point. What is the speed at this operating point? We know that, now we will write at, let us call this point as A. At A, which is the operating point, speed of drive is omega m A. Omega m A means speed at A. A is the operating point. And we already know that is given by this equation, that is given by 200 minus, what was the equation? Yes, the 200 minus 0.1 TLA. Okay. And we also know that omega m is equal to 2 times TL. Let's call this TL itself. So from this, what is TL? TL is omega m by 2. Omega m by 2 means, okay, so therefore we can substitute it here. Therefore, omega m A is equal to 200 minus 0.1 into TL, load torque. And load torque from this equation is omega m by 2. So this omega m A, let me call this omega m A by 2. So omega m A is equal to 200 minus, what is 0.1 by 2? That is 0.05 omega m A. So I will take it to left hand side. So omega m A plus 0.05 omega m A is equal to 200. So this will give me omega m A times 1 plus 0.05 is equal to 200. So this will give me omega m a into what is 1.0.05? It is 1 plus 0.05 is 1.05 is equal to 200. From this, the speed at operating point A is 200 divided by 1.05. I have calculated it, and it comes out to be 200 by 1.05 is 190.476 radians per second. So omega ma is 190.476 radians per second, and this is the operating point. So this is 190.476 radians per second, right? And how much torque the motor is developing? So this is the speed at this operating point. This is the operating point A. At operating point A, the speed is 190.476 radians per second. And how much is the torque? How much torque the motor is developing? Okay, we know that omega ma, it is given, it is 2 times load torque, TL. A, that is 2 times TEA, because whatever is the load torque, that is the electromagnetic torque developed by the motor. So from this TEA is equal to omega ma by 2. Omega ma is 190.476 by 2. So half of this is, so therefore the electromagnetic torque developed by motor is half of this. It comes out to be 95.238 Newton meters. So this is the torque developed. It is 95.238 Newton meters. So therefore we have identified the operating point. This is the operating point, point of intersection between the load and motor torque speed characteristics. And at this operating point, we have found what is the rated speed of the drive. The rated speed of the drive is 190.476 radians per second. And the motor develops a torque of 95.238 Newton meters, which is equal to load torque. Okay. Now we have to verify whether this is a stable operating point or not. Just from the inspection also you can find whether it is a stable operating point or not, because this is a load torque characteristic. It's dTL by d omega m, its slope will be positive, and this is the motor torque speed characteristic, its slope is negative. And since dTL by d omega m is positive and dt by d omega m is negative, so dTL by d omega m is greater than dt by d omega m, or in other words, dTL by d omega m minus dt by d omega m is greater than 0. So by inspection itself we can say that the drive is stable. But let us try to numerically find it out. So now, what is dTL by d omega m? The slope of the curve is the change in the speed, change in the torque with change in the speed. Okay, speed is changing from 200 radians per second at no load to 190.476 at full load. Okay, and torque is changing from 0, because the load torque at 0, at omega t equal to 0, load torque is 0, motor torque is also 0. So torque is changing from 0 to rated torque. And what is rated torque? 95.23. So this is equal to full load torque, no load torque, TL no load, minus TLA, that is full load. What is the torque at operating point A? Full load torque, you can call that, minus what is the speed? Omega ma at no load minus omega ma. So dTL by d omega m is equal to, what is no load torque? At no load, TL is 0, so T is also 0. So it is 0 minus, what is the torque here? We have already calculated it just a few moments back. It is 95.238 divided by, what is the speed at no load? At no load, the no load speed is 200. So it is 200 sorry, speed is also 0, because this is the load torque speed characteristic. When torque is 0, this is the speed is 0, torque is 0, speed is also 0. Speed minus, what is the speed at full load at A? Just few moments back we have calculated it is 190.476. 190.476. So it is minus 95.238 divided by minus 190.476. Minus and minus goes. So it is 1 by 2, that is 0.5. So this is, so therefore dTL by d omega m is 0.5. Just note it down. It is plus 0.5. What about dt by d omega m? Let's try to find out change in motor torque with respect to change in speed, dt by d omega m. So it is equal to motor torque, no load torque, minus motor torque at operating point A divided by motor speed, that is no load speed, minus full load speed. So what is no load torque of the motor? When load torque is 0, motor also develops 0 torque here. At omega t equal to 0, torque, you can see torque is 0. 0 minus how much torque it is developing at A? It is 95.238. What is the motor's no load speed? See, load's no load speed is 0, but motor's no load speed is not 0. Motor's no load speed you can find from torque speed characteristic of motor. It is 200. 200 minus, and what is the speed here? What is the speed here? It is 190.476. So this is minus 95.238 divided by 200 minus 190.476 comes out to be 9.524. So this is minus 9.99. So this is nearly equal to minus 10. So therefore dt by d omega m is equal to minus 10. This is dTL by d omega m. So therefore dTL by at A, of course, d omega m is equal to 0.5, and dt by d omega m is equal to minus 10. So clearly the dTL by d omega m, dTL by d omega m is greater than dt by d omega m. So therefore dTL by d omega m is greater than dt by d omega m. So therefore it is a stable operating point. Or you can say dTL by d omega m minus dt by d omega m is greater than 0, because 0.5 is greater than minus 10. So therefore A is stable operating point. So it is stable operating point. So therefore, with the help of this numerical problem, we have proved that the operating point of this type of load torque characteristic of load and of this type of torque speed characteristic of load and motor, the operating point A is a stable operating point. In a similar way, if you are given torque speed characteristics of load and torque, load and motor, you can find the operating point, and using this logic, you can find whether the operating point is stable or not. If the slope of load torque is greater than slope of motor torque in general, then you can say dTL by d omega m minus dt by d omega m is greater than 0, or dTL by d omega m is greater than dt by d omega m, and hence the drive is stable drive. The operating point is stable operating point. Otherwise, it is unstable operating point. So I hope I have been able to discuss and explain how we find the operating point of a drive, and how do we find whether that operating point is stable operating point or unstable operating point. Okay, and mathematically also we have proved that if this condition is fulfilled, then the operating point is stable operating point. Otherwise it's unstable operating point. So therefore, whenever you design a drive and you find the motor torque speed characteristics, the load torque speed characteristics, you plot them, find the operating point, and using this logic you find whether the operating point is stable or unstable operating point. Okay, if the operating point is stable operating point, go ahead with the drive, design the drive, and then the drive will operate stably. Otherwise you may have to choose a different type of motor for that particular type of load, which gives stable operating point. And with the help of this numerical example also, we have try to learn how to find whether a particular operating point is a stable operating point or not. If this condition is true, then the operating point is stable operating point. Otherwise, it is not a stable operating point. So with this, I will end my today's lecture. Thank you.